Hello everyone, and welcome to today's webinar, Critical Point Drying Workflows for Electron Microscopy. I am Cassie Saltman of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Leica Microsystems. To learn more, visit www.leica-microsystems.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Submit. We'll answer as many questions as we have time for at the end of the presentation. Also, if you experience any technical issues, you can utilize this Q&A box and we will assist you directly. I'd like to now welcome our speaker, Andrew Lawson, Product Performance Manager at Leica Microsystems. Andrew, you may now begin your presentation.
Hello, and welcome to our webinar. Today we'll focus on critical point drying workflows for electron microscopy. My name is Andrew Lawson, and I am an advanced workflow specialist with Leica Microsystems. So I provide application support on critical point drying and a number of other products that we offer at Leica. So first, why use electron microscopy? And if you're joining us for the webinar, you likely are already well versed in electron microscopy. But electron microscopy is a technique that allows you to produce high-resolution images of your samples. It's often used in life science for the study of structure and ultrastructure, of plants and human tissues. On the material side, we look at pharmaceuticals, semiconductors, and a number of other types of samples in material science applications. But electron microscopy gives you the possibility to compare and understand local structural changes in your samples under different treatments or at different developmental stages of your sample. However, you likely already know that to obtain high quality, high resolution electron microscope images, typically the high quality sample prep is key. You need to load a good sample to get a good image out. Okay, so a number of our samples for electron microscopy applications may start as aqueous or hydrated or very delicate samples that when exposed to the high vacuum of an electron beam chamber or electron microscope column, that structure can be destroyed or damaged in some way. So typically, and it's especially common for life science applications, if we're going to do SEM imaging on our sample, we need to preserve the structure and dehydrate the sample to make it more resistant to that high vacuum environment. Okay, so typically, from most applications, our sample needs to be free of water or other liquids prior to being loaded into that EM chamber. Okay, so that brings us to critical point drying. So why would we critical point dry? So here I'm showing a pressure temperature phase diagram for CO2, and we'll kind of ignore that CO2 component and just think about the physics of the phase diagram first, and then come back to why CO2 in just a minute. So here we have again the pressure temperature phase diagram of CO2. You'll see a triple point here where solid, liquid, and gas could potentially exist at a certain temperature and pressure. And then following these lines, we have a solid region, a liquid region, and a gaseous region for our medium. So when we're air drying, and this is a fairly simplistic visualization of an air drying process where we're going from a liquid to a gas. But what's really important is that we're crossing this phase transformation line at some point. Whenever we cross a phase transformation line in a phase diagram, typically we're going to experience a volume change. And so when we air dry a sample directly, crossing that phase transformation line, we will typically get a volume change, and that will negatively impact the structure of our sample, as shown by the water flea that's been air dried here. So what we do in a critical point drying process is we have our medium in a liquid phase. We increase simultaneously the pressure and temperature of our medium in a vacuum chamber, And that gets us into this supercritical range, which is kind of a metastable state. We don't cross a solid phase, a true phase transformation line. We go into this supercritical range through this kind of pseudo phase transformation, you might think of it as. Once we're there, we'll then hold temperatures stable and slowly gas or exhaust down to atmospheric pressure again, also crossing a pseudo phase transformation line here. This is represented by the dotted line here. And we'll be left with a dry gaseous sample. And that, because we're not crossing any phase transformations, any solid phase transformation lines on our phase diagram, we avoid that volume change, and we're left with a much better preserved structure. Okay, so now we'll talk a little bit about why CO2. Again, for life science applications, most of our samples are probably are going to tend to be water-based. You'll see the critical point for water, though, is at a very high pressure, very high temperature, very aggressive conditions that would likely, most certainly, result in our sample becoming damaged or destroyed. So what we first do is replace that water in our sample with something like some intermediate solution, say ethanol or acetone. This is very common. These are very common dehydration media used in life science preparation already. The problem with both of these, although the pressure is much more compatible with sample prep, the temperature is still quite high. So we then do one further step. We exchange that ethanol, for example, with liquid CO2, which has a much more amenable, appropriate critical point for this critical point drying process. You may be wondering why we don't go from water directly to CO2. And the problem there is that water and liquid CO2 are not miscible. So it would be very difficult to fully displace the water in our sample with liquid CO2 prior to drying. And then again, we would be likely left with some damage to our structure. So typically we'll go from water, replace that with an intermediate solvent like ethanol or acetone, replace the ethanol or acetone with liquid CO2, and then complete our drying process. Okay, let's talk about the workflow for critical point drying in a bit more detail. So typically, we will start with a chemical fixation, usually glutaraldehyde or paraformaldehyde, something like that. Then we'll do a dehydration series where we increase the concentration of our solvent, ethanol, for example, while decreasing the water content in our sample. We can then, once we have pure ethanol, purely dehydrated sample, we can then proceed with the critical point drying process. And then we can coat our sample, say via metal sputter, for example, and then perform SEM imaging. We can achieve these processes via a more manual approach or a more automated approach. And when I say manual versus automated, I'm primarily talking about this first few steps, the chemical work. We can either do this kind of by hand in a fume hood, for example, manually exchanging our samples through these different solutions, or you can use a more automated tissue processing machine. Leica has the EMTP, for example. For the rest of the steps, again, it can be fairly automated. Leica has the CPD300 and our ACE line of coaters. They're very automated. You may have other machines in the lab that have similar or less degree of automation, but as far as the manual versus automated processing is concerned, we're typically talking about this first chemical processing step. Okay, so the Leica critical point drying workflow may typically start in our EMTP if you're using our tissue processor. Again, you could certainly do this by hand in the hood if you like. We have some sample holders for the TP that can then be loaded directly into the CPD300 for critical point drying, and then we can move on to our ACE coater to sputter or carbon coat our sample. Okay, so starting with the EMTP, just a couple notes on our process here. So this is our automated tissue processor. Through automation, we can eliminate a lot of inconsistencies that might be caused by manual sample prep. And we can also reduce that manual handling by about 75% compared to a standard manual approach. That automation also offers or allows us to reproducibly process our samples. And also we can, through our different sample baskets, we can process many tissues in a single run, increasing our throughput and decreasing our handling that's necessary. We can also maintain the environmental conditions during the processing, including temperature. Okay, so the TP, it's basically a carousel-based system. So each of these circles here that you see, they represent the position of a vial. So we have this particular carousel can have 24 vials that are 20 mils a piece. And those can be those are typically loaded with for example, your fixative, your ethanol series. If you were doing ultramicrotomy, for example, you could take this all the way through a resin embedding step. This unit here is the temperature module, so it allows you to heat or maintain the temperature of the processing. And over here, this little piece is the stem onto which our sample baskets can be loaded, and these have various sizes, various divisions to allow you to isolate your samples. But once your samples have been processed through the TP, say through your pure ethanol step, that whole basket assembly can be moved directly into the critical point dryer and dried directly. Okay. Yeah, and that's again what I just said. Once we have our dehydrated samples, we can load them directly on this TP stem right into the critical point dryer. So that brings us to the CPD 300. Again, this is another touchscreen-based, computer-controlled preparation tool. Features a quick lock chamber with no tools necessary to load and lock samples in. The only facilities required for the CPD 300 are a CO2 cylinder to provide CO2 and 110 volt electrical power. It sits at a very compact footprint on the benchtop, and it has its own built-in liquid waste collection bottle. We'll typically, for most things, we'll use this aluminum process vessel into which we'll load our samples, and we have a wide variety of sample holders to accommodate many different types of samples that you might be processing. So I'll show a couple examples of our sample holders here. This one I already mentioned. This is the EMTP stem holder. So into this kind of Teflon cylinder, we'll load our basket assembly. If you were growing cells, for example, on TEM grids, you can load grids directly in this holder. We have a similar holder for cover slips. So if you were growing cells or you deposited samples on cover slips that you needed to dry, we have a couple of holders dedicated to those. And then we have a number of holders with different mesh baskets and things. So you can load larger structures into these baskets. Similarly, if you have a powdery type sample or catalyst particles or different frameworks and things, we have a filter disc and porous pots holder with a minimum, at least the Leica offered minimum pore size of 1 micron. So you can load fairly small particles into these filtering vessels as well. Okay, I'll touch quickly on the CPD 300's filler concept. So when we're loading our chamber and loading things into our process vessel here, we can either load actively dried sample holders, things that we want to critical point dry, things that will hold samples that need drying, or we can load blank fillers. The reason we do that is this allows us to kind of tailor the effective chamber volume for drying. So in the software here, we'll key that in. So this blue-green sample holder occupies half of our chamber volume, and then we'll put a couple of fillers on top that will be basically blank. And we'll tell the software that we only want to dry over half of the chamber volume. The benefits here is that it will significantly reduce the CO2 consumption during processing, and it will also help reduce the total processing time. And the CPD300 software is smart enough to take into account this volume to optimize the drying process over just, let's say, that bottom half of the chamber. Okay, again, because we have an automated system here, we can run the same drying process on many samples and get very similar results. We have a large library of recipes available, so you can store many recipes for many different types of samples that you might be working with. And again, you have visual control. You can see what's happening at every step of the process. At a glance, you can see what the process is doing. There'll be a readout of remaining process time as well during processing, so you can quickly monitor while you're walking through the lab, see where the process is at. It's a very simple to use, intuitive system to set up programs and to run them. And it also has a USB interface that allows you to transfer your parameters to and from USB and to allow for software updates if needed. Okay, another comment on reproducibility. So this is just an example. These are 4 independent runs, and these are nuclear pores from a clawed frog. And you can see these are very, very tiny, let's say about 100 nanometers in diameter. So these are very small, very delicate, and slightly difficult to dry samples. But with the automation of the critical point dryer, the CPD300, you're able to get very similar results over multiple different runs, even on these relatively more difficult to dry samples. Okay. So once we have our sample, it has gone through the tissue processor through dehydration, gone through the critical point drying to remove all liquid from the sample. Now we're ready to coat our sample. And so coating is maybe not necessary for all SEM imaging applications, but there can be some benefits specific to critical point drying workflows. So of course, metal or carbon coatings can help reduce charging during imaging. Metal coatings can also help prevent thermal damage from the electron beam. But specific for critical point dried samples, doing a coating shortly after the critical point drying process can help kind of create a barrier to protect that sample from moisture within the air and the atmosphere. At Leica, we have 2 different coating systems. We have the ACE600 here on the left, the ACE200 on the right. I guess the primary difference is the ACE600 is a high vacuum coater. The ACE200 is a low vacuum coater. They're both capable of doing metal sputtering, carbon evaporation, or both within a single unit. But in general, the better the vacuum, the better the coating will be. So we'll talk briefly about the ACE600. So again, this is our high vacuum coater. It's capable of doing metal sputter, carbon thread evaporation, and or e-beam evaporation. So you can choose how you want to configure your tool. Like the other 2, like the TP and the CPD300, the ACE600 is also programmable for automated operation to allow you to get to achieve reproducible films every run. Again, very small footprint on the bench. What you see in this image is essentially what needs to go on the bench top. The pumping system is oil-free and integrated within the housing of the tool. You just need power and potentially argon or nitrogen gas, depending on what configuration of coater you have. It features a 3-axis motorized stage, so the program can adjust the working distance or the height of the stage, the tilt of the stage, and the rotation. Every ACE600 comes standard with a quartz crystal monitor, which is at the center of the stage there. This will monitor and measure your film thickness and also terminate the process based on your desired thickness. The ACE600 can also accept several optional upgrades, including a Meissner or cold trap, a cryo vacuum transfer system if that was needed for certain applications, freeze fracture, etc. Okay, so I'll talk a bit about choosing a sputter target and optimizing your coating parameters. For most critical point drying applications, I would typically find myself using metal sputter over carbon. And you have many metal options to choose from. Couple that I've listed here are gold, palladium, platinum, iridium, chromium, aluminum. The grain size of your film will first and foremost depend on the material that you choose. There's a natural kind of grain size that these films tend to develop. Some of your targets may tend to oxidize in the air, and that's again a material dependent situation. So things like chrome, aluminum, tungsten, they oxidize naturally in air, readily in air. So those usually require a pre-sputter step to clean the oxide, remove the oxide from the target, and that can be built into the A600 program. They typically require a deeper base vacuum, so a little bit longer pump down to really get a deep base vacuum to achieve a nice coating. But I would say the biggest problem with using these oxidizing targets is that they will oxidize, immediately after you vent the chamber and pull your coated sample out. So they should be imaged relatively quickly. So while they're less expensive typically than some of the more inert metals like gold or platinum, something like that, the downside is that they should be imaged relatively quickly if you're going to use a sample that oxidizes. Some other process considerations would be base vacuum, and I already mentioned the better the base vacuum, the better the coating tends to be. The film thickness itself will affect the grain size in the sputtered film. Sputter rate as well will influence the film quality, and your working vacuum. So the argon pressure, the argon gas content during sputter will affect your film somewhat. And I have some examples of sputtered films showing some of these different relationships. So first, the effective target material. So here I'm showing 4 different of the inert metals. So gold, palladium, platinum, and iridium. These were all of these films were deposited under very similar conditions to a thickness of about 4 nanometers. So you'll see first gold, very common sputter target choice. But by taking gold and alloying it with a little bit of palladium, so the target that Leica offers is 80-20 gold to palladium, you see a very marked improvement in basically the coarseness of the film, a decrease in that grain size from gold to gold palladium. Taking it a step further, if we go to platinum, we can get a small improvement over that gold palladium, and then going to iridium, we get a very fine grained film. In my experience, iridium is widely considered to be the best sputter target choice for high resolution work because you can achieve such a fine grain structure. So when I'm working with high resolution applications, I typically prefer iridium. For most other kind of generic applications, I typically go with the gold palladium. Yeah. Okay. Next, so the effect of film thickness. So this is a platinum palladium series of films. And again, prepared under very similar conditions with the variable being increasing final sputtered film thickness. So from 1 nanometer to 2 to 4 to 6 nanometers. And you can see as the film thickness increases, so also does the grain size of the film. So in general, my recommendation is to go as thin as possible, depending on the application, of course. So if we have a very smooth, very flat sample, going thinner, 1 or 2 nanometers, 3 nanometers maybe, especially for high resolution work, would be my recommendation. If we're going, if we have a lower resolution need, a lower resolution imaging need, but we have a highly topographic sample, like a full insect, for example, 1 or 2 nanometers certainly won't be enough, or typically won't be enough to, completely reduce the charging that might occur. You won't get full coating on all those topographic surfaces typically. There we might need to go a little bit thicker, maybe 6 or even more, maybe 10 nanometers, for example, to effectively reduce the charging. But that said, if we're looking at a full insect, we're typically not, needing to go to such high resolution. You can see the scale bar here is 200 nanometers. That's typically not, we're typically not commonly going to such high resolution for, large scale insect imaging, something like that. Okay. The next, I have an example of the base vacuum effect here. So this is 1 nanometer of platinum sputtered either in the 10 to the minus 5 millibar range or 10 to the minus 6 millibar range. So again, as I said, the better the vacuum, the better the coating will be. You can see this is a much more finely grained film than the 10 to the minus 5 example. But again, that said, this is at 650x magnification. It's, in my experience, very rare that we need to go this fine. So if we're doing lower resolution work, we might be just fine in the 10 to the minus 5 range. It just depends on the imaging that we need to do, the structures that we need to see on the sample. So yeah, the main trade-off here, going to a deeper vacuum, you get better quality, but it will take more time. So if we need high resolution imaging, it certainly may be worth it to go to this deeper vacuum. But if we're doing lower resolution work, we can get away with a shorter pump down time and a slightly more coarse film. Okay, I think the final example here is the effective deposition rate. So this is a gold palladium film, 2 nanometers thick, deposited with either 15 milliamp sputter current or 60 milliamp sputter current. So the higher sputter current here will lead to a faster deposition rate, which will again lead to a more coarse film. So simply by decreasing your sputter rate here, your sputter current, you can get a little bit more fine resolution out of the film at a relatively small time increase, in my experience. Another parameter that can effectively be used to tailor your deposition rate is the working distance. So a shorter working distance will lead to a faster sputter rate, similar to the 60 milliamp example here. Whereas a longer working distance will lead to a bit slower deposition rate. So my preference when using the A600, for example, Leica has, for each of the sputter materials we offer, Leica has a recommended sputter current. I typically start with that sputter current and use my working distance as my primary tuning factor for sputter rate. And then if I need a kind of a secondary tuning factor, then I would play with sputter current personally. Okay. So now I have a number of examples of actual critically point dried samples. So this is a first set of examples is from a tobacco leaf. So plant sciences. So we have a tobacco leaf. You see the stomata and the stoma are well prepared, well preserved. We see quite a number of applications for marine biology as well. So this is a marine worm, first chemically dried here and then critically point dried. The chemical drying preservation is not too bad, but the critical point dried sample is preserved much more finely. You can also see the cuticle here with muscle fiber, as well as some bacterial cells that have been well preserved as well, which likely, and I would say likely these finer structures, although they're not shown on this chemically dried worm, some of this finer structure I think is likely not as well preserved on the chemically dried sample specifically. Okay, an example of black mold here. So these are, again, fine structures, very fine structures. You can see some of these kind of filaments here even are still preserved there. We don't see much deformation in these structures that I would expect if the drying was less efficient. And then a couple of material science examples. So this is a kind of a metamaterial microstructure that when air dried can see significant deformation of the structure, but retains its structure when critically point dried. And a final material science example, this is a zone plate that's used for focusing X-rays and synchrotron applications. It's made up of these very, very small kind of lattice structure, maybe about 100 nanometers in height here. And prior to being employed in the synchrotron, it's critically point dry to clean it to make sure it's free of debris, but maintains its very regular, very fine structure. Okay. So those were just a few examples. We also have an application booklet that's available for download from our website with a number more examples. And one of the nice things about the application booklet, it talks a bit about what sample holder was used, but about the chemical preparation as well. And then it includes the critical point drying recipe in addition. So a good resource for other examples of samples that have been prepared or could be prepared, and a good jumping off point to help you get started with your samples as well. Okay. And again, that can be downloaded from the Leica website. So that concludes our webinar. Thank you again for your time and attention, and I'll take any questions at this point. Thank you very much.
Thank you, Andrew, for your informative presentation. We will now start the live Q&A portion of this webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box, and we will answer as many of your questions as we have time for. Let's go ahead and get started, Andrew. Our first question asks, what transitional fluids can be used on the CPD?
Yep. So there are 3 that can be used in our critical point dryer. They are ethanol, acetone, and isopropanol.
Okay, wonderful. Thank you so much. Our next question here asks, what types of materials can I coat with?
Yep. So in the A600, you can configure it with 2 sources basically. And so maybe the most common configuration would involve 1 sputter source and 1 carbon source. For metal sputter, there's a slew of materials. I talked about many of them in the presentation today. But yeah, there's a good 8 to 10 or so kind of standard metals that you can coat with. And then on the carbon side, it's really carbon. We have either carbon thread or E-beam evaporation available. And I think there's a question about E-beam as well, so I'll go a little bit deeper into that. So E-beam it's essentially an indirect coating method. Rather than running current through the carbon rod or through carbon thread, we run the current through a tungsten filament, which ejects E-beam which ejects electrons into the carbon rod. The benefit of E-beam is that it tends to give a finer coating. So really high resolution work, you might go with E-beam. It's also directional, whereas sputter, carbon rod, carbon thread, they're not truly directional coating methods. E-beam is more directional, so you can do things like DNA shadowing or replica work because of the directional nature of the coating.
Okay, wonderful. We have another question here that asks, why is that oxidation of cheap targets a problem for coating? I guess the innermost layer of the film remains conductive.
Yep, it's a good question. I would say that especially for higher resolution work, we're usually looking, at the surface itself. And so if the outermost surface of your film becomes oxidized, even though the inner layer of the coating is not oxidized, essentially, the charge dissipation behavior of the film will just not be as good, especially for these this type of situation. We're probably putting down a very thin coating as well, so proportionally there's a bit more oxidation, I guess, in that case. So again, for your application, it may not be so detrimental, but it's a consideration to think about, especially for high resolution work.
Okay, excellent. We have another question here that was submitted. This question says, I usually use ethanol for my plant samples. What samples do researchers use acetone or isopropanol for dehydration?
Yep, it's a good question. I would say most of the time, ethanol is the choice for most samples. Isopropanol, I don't usually see for life science work. I might see some isopropanol if we're looking at material science type samples. And then acetone, I really only see once in a while as a transitional fluid. Again, it might be a bit more common on the material science side versus life science, but so I can't really say offhand which samples would call for acetone. In my experience, it is mostly ethanol as the option.
Okay, excellent. And then it looks like those are the questions that were submitted here during our live. If anyone has any last minute questions, feel free to shoot them off now. Before we wrap up, I did want to thank you, Andrew, for your time today and your important research. And we would also like to thank LabRoots and our sponsor, Leica Microsystems, for underwriting today's educational webcast. I'd also like to thank the audience for joining us today and for their interesting questions. Any questions submitted during the on-demand period will be addressed by our speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, take care, everyone, and goodbye.